Okay, in this video, we are going to find all of the octahedral isomers with the formula MA3B3. M is a generic central atom, usually a transition metal, and A and B are unique monodentate ligands. And so the way to do this in a systematic fashion is to track trans pairs and to do this alphabetically. So we think about what pairs are across from one another of these six ligands. And so to do this alphabetically, the first one, well, we have three A's, so we're going to start with AA. And then the most alphabetical arrangement is going to be AB. Um, and from there, we're forced with our last arrangement to be also, BB. So we have three B's. So that's one arrangement. After we do AA, we can try to do AA again to keep things as alphabetically as possible. At this point, we never want to write our next alphabetical. We don't have any ACs, so there's no C's in this molecule. And so our next one will do BA, perhaps, but that's the same as AB. So if you write one in reverse alphabetical order like that, our rules are just going to say, don't do that. That's not a unique one. So never write it in reverse alphabetical order for any trans pairs. So we don't have any BAs. Our only other option, therefore, would be BB, but that forces this to be AB, which is just what we wrote above. So we're just going to cross that out. So that tells us that, we've done all the AAs, and so now we're on to starting with AB. And with AB, we could write alphabetically AA, and that would force this to be BB. Well, that's just what we wrote up above, but in a different order, so that's not unique. So let's try a different AB. Instead of ABAA, our next alphabetically would be ABAB. And then this will force this to be AB as well. And that actually is unique from above. Okay. Once we do that, we can try to continue with the ABs. We do AB. We've done AB, so next will be BA, but that's a reverse order. So that's not allowed by our rules. So now we'll be ABBBB. That's good. And this would force that to be AA. But notice that that's just what we had at the top. Just the three trans pairs are ordered differently. We don't care what order the three trans pairs are. They have to be three unique trans pairs to be unique isomers. So that's out. And at this point, we've exhausted all the ABs because all the ABs, because BB is the last one in the alphabetical list. So that forces us then to go to the B's, starting with the B's, because we did all the A's, right? We did AA and AB. So we could try BA, but again, that's a pair in reverse alphabetical order, so we don't want that. So we're forced only to do a BB. BB would give us AA as the highest one alphabetically, which would then force this to be AB, but we already have that as our first listed one. And so BB, we could try AB, that forces this as AA, but that's just the same as above. Just the last two switched, and then from there on, we're basically done because we have BB, and the only thing we could do left would be BA, but that's again having a trans pair in reverse alphabetical order. So this is the systematic way to prove that there's only two isomers for MA3B3. And let's now draw those isomers and talk about them a little bit. So we have structure 1 here, we have structure 2 here, and we're saying, hey, we have an AA trans pair. So A and A are across from one another. We now have an AB trans pair. So A and B are across from one another. And we have a BB trans pair. So B and B are across from one another. So that's our structure number 1. Structure number 2 looks a little bit different. Now we have AB, AB, and AB across from one another. So we write an A and a B across from one another, an A and a B across from one another, and an A and a B across from one. And these are our two isomers. Now, we can ask, are they chiral? And they are not chiral. The reason why they are not chiral is because there are mirror planes. And so um, if anytime you have an AA, two, or a BB, two of the same monodentate ligands trans from one another, you're going to have a mirror plane that you can draw. So the mirror plane, one of the mirror planes in this molecule is right here. It contains M, B, B, A, and B, and A is looking at another A itself in the mirror. So this is a mirror plane, so this is achiral. And for this molecule, we also have a mirror plane. We can't draw the same mirror plane because A would be looking at B, so that's not a mirror plane, but we have one that is sort of cutting through right there. So this A is looking at itself in the mirror, and this B is looking at itself in the mirror, and the mirror contains A, M, and B. So that's also achiral, meaning it's not chiral. So if your molecule has a mirror plane, it can't be chiral. All right. These two isomers have names. They're very common in inorganic chemistry. So we give these two isomers names. They're called the FAC and the MER isomers, or FAC and MER. Okay, so this one is the meridional isomer. We abbreviate that with MER. And this one is the FAC isomer, or the facial isomer, that's the abbreviation. And the reason why they're called this is the three A's and three B's are on one face of the octahedron. And so there's, if you draw out the octahedron for this, these are basically on one face. There's a C3 that you can actually rotate, okay, 120 degrees. You can rotate this molecule to symmetry. And so these A's are also on the same face. This is called the meridional isomer. It's like the prime meridian of the globe, right? One of the meridians. And you can see they're sort of in a belt. So these three are in a belt, and these B's are also in a belt. So those are the two isomers. We did this in a very systematic way. And what this will do is it will allow us to come up with more complicated examples and solve those sorts of problems. So check out the other videos for that.